Good day everyone. In our previous lecture, we discussed about the takeoff, landing and cruise flight of a drone. Similarly, in our current lecture, we will be looking at the next set of principles which are hovering, forward and backward motion and rotating the drone. These are the principles required for moving the drone from one place to another. Let's look at these principles in details in our upcoming slide. In our previous lecture, we looked at the concept of takeoff and landing. Our present concept involves understanding what is hovering of a drone. Let the drone have a mass m in kgs. The drone's weight is mg, where g is the usual gravitational constant. I am standing on the ground and my weight is force pulling me down, but I don't fall downwards because the ground is supplying an equal and opposite force upwards on my shoes. Imagine I am holding up a drone in still air with rotors switched off. If I let it go, it will start to fall to the ground since it has a weight mg that acts downwards and there is no balancing upward force. To allow it to hover, the rotors must be switched on at such a speed as to provide an upward force of mg. They do this by pushing air downwards and the air exerts a reaction upwards, Newton's third law. This reaction is in fact a pressure change across the rotors and is a reminder that much of the force moving a drone is exerted through the rotors. They need to be strong enough to do the job. So the rotors pull the drone along and apply their pull through the motor spindles. If any of the threads that hold the plastic rotors onto the metal spindle are not in a good enough condition to transmit this pull, then the failure will result and the drone will almost certainly crash. Hovering is when the force produced by the rotors balances the weight of the drone. So basically, the net force is zero acting on the drone, and the drone stays in one place in the air. As you can see in the equations also, F1 plus F2 plus F3 and F4 balance out the weight of the drone. This provides an overall understanding of what hovering actually is. We can see how the drone can stay in midair through hovering. Let's see at how the drone can move forward or backward or sideways direction. If you want the drone to move forwards or backwards, you slow down two rotors on one side of the drone and speed up the two rotors on the other side. The drone steps slightly towards the slower side and moves in that direction. This is according to Newton's third law of motion, that every action has an equal and opposite reaction. If you want to move sideways or backwards, we just use the same principle on other sides of the drone. With the propeller plane moving forward, the air screw is at right angles to the direction of motion, which makes looking at the flow of air past the propeller simpler. With the drone, the rotors are steeply angled to the direction of travel. I think we can avoid looking at the airflow. First, we'll look at things from the point of view of someone moving with the wind. If there is no wind, this will be the same as being on the ground. Otherwise, the ground will be moving past, but that won't affect the physics of what's at the drone. Moving the drone horizontally at a steady speed relative to the air, power is needed to work against the frictional drag of pushing the air out of the way and past the drone. When traveling at constant speed, the drone has to provide an equal and opposite force to drag. It does so by tilting so that the reaction force the air exerts on it now has a horizontal component. Of course, the vertical component is now reduced a bit so that the rotors must work faster to make good the loss of vertical component if the drone is not to fall. At least that would happen in the absence of any lift being produced by the forward motion of the drone. If you look at the profile of a drone, it is curved at top and less so beneath, a bit like a wing of a plane, though with a very broken profile. I suspect there is some added lift from the forward motion, but also I suspect it's not much. A model glider shows how effective aircraft wings are. Throw the glider forward and the lift supports its weight or almost so. Throw a tilted drone forward and it has no useful gliding capability and hence no useful wing lift. In the spirit of making approximations, I will ignore any lift on the body induced by moving the tilted drone through the air. Returning to the basics, the faster the horizontal speed needed, the more the drone tilts to increase the forward force. The rotors are a moving surface that is angled up into the wind and pushes the air backwards. Tilting into the wind, though, reduces the angle of attack of the drone, reducing their capacity to produce thrust. The faster the drone goes, the less thrust is available for the rotors. So there is a speed limit from which this effect as well as from the drive of the drone through the air. The current video shows how the drone actually tilts forward when it's going in that particular direction. This will give you a proper understanding of the physics that we were talking about till now. We know now how to move the drone horizontally, but what if we want to turn the drone in a particular direction? Let's look at it using the picture shown in the slide. In this diagram, you can see the quadcopter motor configuration where 2 and 4 motors are rotating counterclockwise and 1 and 3 motors are rotating clockwise. With the two sets of quadcopter motors configured to rotate in opposite direction, the total angular momentum is zero. Angular momentum is the rotational equivalent of linear momentum and is calculated by multiplying the angular velocity by the moment of inertia. What is the moment of inertia? It is similar to the mass, except it deals with rotation. Angular momentum depends on how fast the rotor spins. Conceptually, moment of inertia can be thought of as representing the object's resistance to change in angular velocity. If there is no torque on the quadcopter motors, the total angular momentum must remain constant, which is zero. To understand the angular movement of the above quadcopter, think of the 2 and 4 counterclockwise rotors having a positive angular momentum and the green clockwise quadcopter motors having a negative angular momentum. I'll assign each motor a value of -4, +4, -4, and +4, which equates to 0. To rotate the drone to the right, then decrease the angular moment velocity of motor 1 to have an angular momentum of -2 instead of -4. If nothing else happened, the total angular momentum of the quadcopter now has a +2. Now that can't happen. The drone will now rotate clockwise, so the body of the drone has an angular momentum of -2. Decreasing the spin of rotor 1 did indeed cause the drone to rotate, but it also causes a problem. It also decreased the thrust from motor 1. Now the net upward force does not equal the gravitational force and the drone descends. Also the quadcopter motor thrust are not the same, so the quadcopter now is unbalanced. The quadcopter will tip towards in the direction of motor 1 to rotate the drone without creating the above imbalances, then a decrease in the spin of motors 1 and 3 with an increase in the spin for motors 2 and 4. Therefore, to summarize, when you want the drone to turn, you slow down two of the diagonal motors and you speed up the other two diagonal motors. Remember how the motors next to each other are spinning in opposite directions. So by slowing down two going in one direction and speeding up the two going in the other direction, the drone will accelerate as fast as possible from the ground depending on how fast the propellers rotate. The lift will remain constant, so the drone doesn't change height, but the angular momentum is increased, so the drone will turn in place. To summarize, we had a look at three main parts of flying a drone. First is hovering, second is forward and backward motion, and third is rotating a drone. This will allow to move the drone from one place to another. While doing all these maneuvers, we have to make sure that the drone is stable. But what is stability and how does a drone remain stable during these operations? Let's look at stability and gyroscopic effect in our next chapter. Thank you very much.